Hi, this is Dr. Mahmoud Al-Odeh again, and in this video we're going to talk about the second phase of Lean Six Sigma, or in particular Six Sigma. We haven't started Lean. In the second phase of the Six Sigma methodology is the measurement. The measure phase where we start collecting information and we start collecting data. The input for this phase comes from the output from the previous phase, the define. As you remember, we talked about the define phase where we start collecting information about the problem, define exactly what the problem is, and we use the high level of the process map. We need to see the flow of the process in order to identify the problem. So let's go ahead and start with this phase. This phase, as I mentioned, will need the project charter. You have to have the problem statement. You have to have the matrix, what kind of measures that you're using in order to verify this, this problem. Also, what you need to know, the responsibilities for your team. So you have to have a team and you have to have some responsibilities for these teams. From the beginning, you should be able to understand who is responsible for these projects. Again, the input will be project charter, the scope, the timeline, the resources, the budget. Second, we have to have the rules and responsibilities for your team. Third, you have to have a clear problem statement, what exactly the problem, and could be identified by the process map or the flow chart. We talked about it in a previous video, and we need also to define what measures that we're using in order to define the problem. For the tools that we're going to use in this phase, the measure phase, we're going to use some data collection tools. We have to use some measurement scales. We have to validate the data that we've collected. We should use some statistical distribution and know based on what data we have, what distribution we should use. Some data mining and data programming if we need to code the data or uncode the data. We should use some charts such as the run chart, the SPC, statistical process control chart as well. We have to have a detailed process map. Now we're talking about the value stream map, extremely detailed with more information about the process. We should have a process cost as well. At the end of this phase, what we're going to have a well-defined process, because we did focus on a lot of details. We have a well-defined process. We will have a baseline process capabilities. We will have something called critical to quality and critical to customers as well. We need to know exactly what are the parameters, the factors that will impact the quality, and focus on these factors. Also, we'll look into the critical to customers. What are the factors that are important to the customers? Now we're looking into two different things. The critical to quality is something it's something we call it the voice of the process, the voice of the process, and this is coming from the process itself. The critical to customer, it's the voice of the customer. Through this workshop and this course, we will be talking about all these concepts in more details. Also, as the output for this phase, we're going to talk about cost of poor quality. As we know that poor quality has a cost. In order to implement a project and justify the cost of a project, we should have some documentation showing the cost of poor quality, or what we call it, the COPQ. And a last thing, we should have a measurement system. Let's go and talk about this in more details. Okay, so starting with the tools that we're going to use to collect the data, it's the something what we call it. It's a simple tool. We call it the check sheet, and the check sheet, it's basically a tally sheet where whenever a problem happen, a defect happen, we check a mark. We say, okay, here's problem number one happened now. So we start checking the marks in order to have some tally checks on each categories. So we have different categories such as, machine breakdown, lack of training problem, uh, dimensions are not correct and accurate. So you create several categories in order to monitor the process. So while you monitor the process, you see a defect, you tick mark, just like a line. You say, okay, here's a line, a tally mark. We're saying, okay, I counted this defect happened on this time. So you start counting these defects. This is the simple thing that we could use in order to justify, or in order to have some baseline for us to implement the improvement. Second thing we're going to talk about it is the run chart. The run chart, it's plots of data arranged in the time or order sequence. So this is what we call the run chart, or the statistical process control chart, the SPC chart. These are data that we get from monitoring the process for long term over the time. Also, the cost of poor quality, this is important, and this is the cost that associated with having some defects in the process, not having the not having the work performed correctly at the first time, and we eventually will receive a low quality products or service. And these are divided into four categories: appraisal cost, internal cost, provincial cost, and external cost. And in the appraisal cost, these are the costs that we apply to monitor and measure the quality parameters. And these are important because we need, because it's associated with the quality audits. These are really important. Uh, these costs will, you know, uh, dealing with problems such as the vendors, the suppliers, and that's why these are important. Internal failure costs, these are associated with correcting the low quality of products, such as long cycle time. If you have a long cycle time, why is that? You have to figure out why is that. Preventive costs also, it's a cost that you prevent problem from happening, such as recall products, audit personnel, and these are really critical and essential, because these are will prevent things from happening, defects from happening. This will prevent the defects from happening. External failure costs, these are also important, but these are related to the cost outside of your organization, such as the poor quality of products on final customer. And these are such as loss of goodwill, write-offs, service problems, warranties. There are a lot of examples on the external failure cost. Okay, again, these are costs associated with defects. If we have a bad quality, what would be the cost? These are the four categories that you could put any cost related to quality in these: appraisal, internal, provincial, prevention, and external. Control and run charts. These are charts used to study the performance of the process over time. The control charts are created by finding the CL, which is the center line, upper control limit, and lower control limit. And then you start monitoring the process. So basically, what you do in order to do in order to develop the control charts, what you need to do, you need to observe a process, and then once you observe it, you start collecting the average. This is the average, would be the center line, the average of the measurement. And then you say, okay, what would be the upper limit and the lower control limit? So you put the tolerances. Okay, what is something acceptable based on the process? Now it's not based on you, based on the process. What's the upper control limit and lower control limit? And there's calculation for that. It's covered in a different class. I would highly recommend that you refer to that if you're interested. As for this Lean Six Sigma certification, you are need to understand just the the basic and idea on what the control charts. So the control charts, again, what you do, you observe the process, you find the average of these measurements, you calculate the upper control limit, and the lower control limit. These the limits are the tolerances for the process, and then you start. These are the basis for your process, and then you start observe the process. And again, if some of these measurements get out of the tolerances, out of the control limits, these are they should be measured, and these should be studied. That why is that happen? Because these are out of control. So this means that more variation in your process, which will result in low quality for your product and service. All right, based on this, we based on the collecting the data, we need to be able, as a Six Sigma expert, you need to be familiar with the different type of data. And why is that important? Because all based on this data, you will be able to select what tools to use. There are a lot of different control charts. Some of them for attributes data, some of them for continuous data. So we need to exactly know what data that I am collecting. Based on what data I am collecting, I will be able to use the correct tool to be able to measure the process. So the data type consists or could be divided into a qualitative and quantitative. Qualitative, it's divided into three parts: nominal, ordinal, and binary. Nominal and ordinal, these are the most common one between them. Nominal, variables with no inherent order or ranking sequence. For example, gender, race, etc. So as long as there is no ranking in the data, this is what we call nominal. Ordinal, these are variables with an ordered series. So you could say, as long as there is an order series, then that's an ordinal, such as blood group, performance. So you start, for example, in the performance, you start with low quality, good quality, high quality. So there's kind of ordering series in there. Binary, these are variables only for two options, such as pass and fail, yes or no. These are kind of what we call the binary. On the other side, the quantitative data, these are the most common that we use it, something that we will see it in real application. As long as the nominal and ordinal, binary is not, I did not see a lot of information on that, but it's still important. However, the continuous data is information that can be measured on quantum or scale. Continuous data have almost any numerical value and can be meaningful, subdivided into finer and finer increments, such as the length, the size, the width. The discrete, it's called the attribute data as well. It's known as attribute data. Discrete data is information that can be categorized into classification. Discrete data is based on count. Infinite number of values is possible, and the values cannot be subdivided meaningfully. For example, number of parts damaged in shipment. Yes, these are counted. These are we can't subdivide these. It's just number of parts that are damaged. Okay, more information about nominal and more examples. So the more examples that I give you, the better understanding for this data. Nominal data labeling variables without any quantitative value. So for example, what is your gender? This is the data that we will get from this survey. It will be nominal. What is your hair color is nominal. Where do you live? There's so, as mentioned here previously, what we did said there's no ranking. As long as there's no ranking, this is a nominal. Ordinal, the second category here on this slide is the ordinal. The order of values is what is important and significant, but the difference between each one is really known. Yeah, so for example here, as long as we're having an order here for the data, this is an ordinal data type. Example on this: how do you feel? As you see, very happy, very unhappy, unhappy, okay, very happy, and very happy. So these are five ordered. How satisfied are you? How satisfied are you with our service? And the same thing, we have a rank. As long as we have a rank, this would be an ordinal data. Next, we're talking about interval numeric scales in which we know both the order and the exact difference between the values, such as the temperature. Example, here you go. Celsius temperature, because of the difference between each value, is the same. Uh, for example, the difference between 60 and 50 degrees is measurable to 10 degrees, as is difference between 80 and 70 degrees. So as long as we know the difference between the values, so this is what we call the nominal. Again, this is the nominal, the interval, I'm sorry, interval data is something that numerical scales, which we know both the order and the exact difference. We give the example of the Celsius temperature uh, as an example for interval. Ratio data tell us about the order, they tell us the exact value between units, and they also have an absolute zero, which always for a wide range of both descriptive and inferential statistic to be applied. These variables can be meaningful, added, subtracted, multiplied, and divided, or what's called the ratios. As an example for this is the Bath scale. This is just a scale. This is kind of an example on the ratio data. This chart will show you some features for nominal, ordinal, interval, and ratio, and you will see the sum of the differences. I'll go with from the bottom to the up. Has a true zero. The ratio data type has a zero. The rest of them, there's no zero for that. Can multiply and divide. The ratio can be multiplied and divide. Next, can add or subtract. The interval and ratio data can be added or subtracted. Can quantify the difference between each value. Yes, the interval and the ratio can be quantify the difference between each values. The mean, can we use the mean? We could use the mean for interval and ratio data. We cannot use it for nominal or ordinal. It doesn't make sense to use the mean, the average, as one of the calculation for the interval and ratio. Median, we could use the median for ordinal, interval, and ratio. Mode could be used for all four categories. Counts or frequency distribution could be used for all of them. The order of values is known, ordinal, interval, ratio. The nominal, as we mentioned earlier, there is no order for these values. Now let's move on into some statistics. As we talked about Six Sigma, it's a methodology based on numbers, based on statistics that will help you to make decisions, will help you to improve quality, will help you to improve efficiency and utilization. In order to become a Six Sigma expert, you have to know some statistics. And the more you know in statistics, you will have a higher level in Six Sigma. So the more advanced statistics you have, the more level you will have. So in order to become a master black belt, you have to basically know all the statistics, advanced statistics. All right, so in statistics, we have basically two broad categories or classification. One is called the descriptive statistics, and the other one is called the inferential statistics. The descriptive statistics, something that you could describe a big chunk of data with summary of charts and tables. But for the descriptive statistic, you don't attempt to draw a conclusion about the population from which the sample was taken. So now we know there is some population, some term in the statistics, something called sample and something called population. The sample is taken from the population. Population is every element of the study. So for example, if you're trying to do a survey for the city of Bemidji, for example, you have to go for every person in the city, which is about 16,000 population. You have to go and ask each one of these 16,000 person to for their opinion. This is in this case we surveyed all the population, all the people in the Bemidji. However, sometimes this is a cost. This is something acceptable, but sometimes it's costly, and you probably need more time. And it's sometimes you get frustrated and you can't finish it. In order to make it acceptable, what would you do? You say, "I'm gonna pick um, uh, 10 people from the north, 10 people from the south, 10 people from the east, and 10 people from the west." And in this case, these will be taken randomly, and whatever I get information, I will apply it for the population. So first of all, I want to make sure that you are familiar with the sample and the population. Their sample is taken from the population. So going back to descriptive statistics, this is describing a big chunk of data based on charts, tables, but we're not trying to draw any conclusion about the population. However, the inferential statistics, it's basically testing a hypothesis. In drawing a conclusion, as long as you're drawing a conclusion about population, this is called inferential statistics. And of course, this conclusion came from studying your sample. In in the hypothesis, we have two hypotheses. One is called the null hypothesis, which is which means no statistical difference between the two variables. So if you study two variables, you say, okay, there's no difference between these two variables. If you say, okay, I'm going to study the income for the east of Bemidji and the west of Bemidji and see if there is a difference. So the null hypothesis, we're saying that there is no difference in income between the city of Bemidji on the north, the people who lives in the north, and the people who lives on the south, or the people who lives in the east and the people lives in the east. So all the time, the null hypothesis, there's no difference. There is no statistical difference uh, between the two variables. The alternative, however, what we say, okay, there is a statistical significance. There is a difference between these two variables. Even though hypothesis tests are meant to be reliable, there are two types of errors. Okay. However, sometimes even what we do, we're trying to study these hypotheses and see if there is a relation between two variables or more. Sometimes we will have some errors. This is what we call the type 1 error and the type 2 error. The type 1 error, it's null. And when does that happen, the type 1 error? And this is really important. You should be aware with the difference between the type 1 error and the type 2 error. The type 1 error, when the null hypothesis is true, but however, you rejected that. You couldn't prove it. You couldn't prove this is true. And this is type 1 error. Type 2 error, when the null hypothesis is false, however, you failed to reject it. Okay, so this is the two types of errors that we see, type 1 error, type 2, and it's based on the null hypothesis. If it's true, but you rejected it, this is type 1. If it's false, but you failed to reject it, this is type 2 error. Some statistical tests that we use in the measure phase called the regression, the linear regression, and we do a lot of statistical analysis using whether Minitab or SPSS. There's so many software that we could use these days to conduct these statistics. But however, let's focus on two things here. And I provided these tables because really important. You need to be able to conduct this, and you should be able to read these values. So let's start with the linear regression. Is if there is a relation between a linear relationship between variables or not. The R here in this table represent the symbol correlation, and this is 8, 0.873, which means that there is a strong relation. As long as you have closer to 1, so 1 means 100% there's a relation. Now we have an 87% 0.3 between the two variables. So we're trying to find if there is a variables or not. Okay, so let's read here. R is 0.873, which indicates a high degree of correlation between price and income. So for this table, we're studying the price and the income. We found that there is a strong relation, a high correlation between these two variables. Now, moving into the second table, what we call the ANOVA statistical test. In the ANOVA statistical test, what we do, we first of all, we have to consider the P to be 0.05, which is the percentage of error. Type 1 error or type 2 error, we need to make sure that we put this is an assumption, and we say P, the probability of having an error, to be 5%. And once you conduct ANOVA analysis, you go to the significant column, to this column right here, and you compare it with the P. If it's less than P, what you do, reject the null hypothesis that there is no relationship. So you reject that there is no relationship between two variables. If it's higher than 0.05, then you accept the null hypothesis. All right, so the model statistically significance predicts the output variables. So since this is significant, we have rejected the null hypothesis. We rejected that there is no relationship, which means yes, there is a relationship. Therefore, we could create an equation. We could create an equation to predict any future prices. What would be the price based on the income? Okay, the equation will be, okay, we're talking about the third table right here. The price equal to the variable here, the constant 8286, plus the income, the slope for the income 0.564 times the income. That will give you the price. So through the statistical tests such as linear regression and ANOVA, we were able to come up with an equation which will help us to predict the price based on the income. It will help us to see if there is a relationship between the price and the income based on the linear regression, based on the significant, based on the p-value, and therefore these are very helpful to help us in the measurement phase. Is there other tools that we could use? Absolutely. The t-test, for example, here's another test that we could use. T-test is a test that if the difference between two or more means. Okay, so for ANOVA and linear regression, we tested if there is a relationship between two variables. For the t-test, we find if there is a difference between two or more means. That's for the t-test. When we measure for the data, we have to consider two things: accuracy and precision. Also, there are other concepts related to accuracy and precision, linearity, and stability as well. These all will related to validation of the data. Why these important? Okay, well, I'm collecting all this data. Are these valid? Are these correct? Is my measurement correct? In order to do that, you have to ensure that you have an accurate data, which means the average value of several measurements taken, or precise data, which shows how the measurements are clustered around the center. spread the measurements, the spread, how far from each other? Are they cluster? Are they all the measurement close to the center, to the data, or not? And we study two R's for the precision: repeatability and reproducibility. Repeatability is the variation observed when the same operator measures the same part repeatedly with the same device. Are we going to get the same result? If I measured the length of this chair right here twice, do you think I'm going to get the same measurement if I use the same tool? Reproducibility is the variation observed when different operators measured the same part using the same device. If I brought my brother here and I said, okay, would you measure this, the length of this table? Is he going to get the same measure that I got? This is what we call the reproducibility. Linearity. How well the measurement system performs over a range of events. Now we have a measurement system. We need to study the system performance over a range of events. Stability. How well does the measurement system performs over time? Okay, is the measurement system will be accurate next year, 2 years from now, 5 years? So this is what we call the stability. You have to be able to define the difference between these four type of categories, and these are really important because you need to see if when you collect the data, are these valid or not. Okay, this chart will show you the difference between accuracy and precision. As you see in the first, on the left, upper left, you will see an accurate and precise. On the right, upper right, you will see it precise but not accurate. On the lower left, you'll see accurate but not precise. On the lower right, you will see neither accurate or precise. This is just to give you an idea on what the difference between accuracy and precision. A really important concept for data validation, we use the gauge R&R study. And this is basically a study of to help you if you need to recalibrate your operation, your machine, or if your newly hired operators are measuring ingredients consistently. Or maybe we need more training to give these new hires. For the gauge R&R study, we use the two R's that we talked about: repeatability and reproducibility. Again, the repeatability is the variation observed when the same operator measured the same part repeatedly with the same device. Reproducibility, the variation observed when different operators measure the same part using the same device. Let me give you an example on gauge R&R study. So we have this first operator. We asked them to observe 25 to take a measurement for 25 parts, and we know which one is valid and which one is invalid, which one is has a defect, and which one does not have a defect. So this is the master attribute. This is already known before, but we need to measure the accuracy of this observer. We need to know if there is a need for training or not, if we need to recalibrate the machine or not. And so we asked the first operator to do 2 trials, first trial, second trial, and measure this and let us know what that operator thinks. So for the first part number 1, the operator measured val and val. So this is an accurate and reliable as well. For the second part, we know that this part is invalid, defect. However, the first operator said this is for the first time said valid, for the second time said invalid. So this is first of all, it's inaccurate. As long as there's no consistency between these are inaccurate and this is unreliable. So this is why the zero coming from. Move on to the third one, to the third part. We know that this is a valid part. However, the first operator indicated in the first trial this is invalid. The second time, he also said this is invalid. Now, is this accurate? No, it's not accurate because it does not match the master attribute. So this is why we have a zero. Is it reliable? Well, yes, because we have the observer have the same thing on the first trial and the second trial. So this is what we call it. Yes, it's reliable. Okay, well, then we conduct all this here. We do the same thing for the 25, just studying the master attribute, compare it to the observer on the first trial and the second trial, and then you decide what is the accuracy for this person, what is the reliability of that operator, and then you make a decision if this person needs to be more trained, or this resource could be a machine, could be a scale, could be something that you use to be able to identify if it's accurate or reliable. Okay, so and then you calculate. So how we do that? You add the numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you'll get that to be 15. Divide that by 25. You will get 60% as a 60% as an accuracy. Reliability, the same thing. You add the ones together, you will see 22. You divide it by 25, you will see an accuracy percentage of 88%, and this is how we conduct the KHR and R. The second tool that we use, or another tool that we use, we covered so many tools so far in the measurement phase. Another tool that we use in the measure phase is the value stream map. The value stream map, it's a more detailed flow chart that will help us to identify the value of the process, and it will help us to identify also the bottleneck in the process and eliminate waste. A value stream map divided into 3 segments: production or process flow, information or communication flow, and the timeline. In the first part, you will see this is the traditional flow chart. You will see the flow of the process, draw from the left to the right. If there are subtasks or parallel tasks, they should be drawn from left to right beneath the main flow as well. So be careful on how would you create the subtask or parallel task. These also created below, right beneath the main flow. Information communication, these are basically the arrows that we see. At the top portion of the map, all the communication, both formal and informal, that occurs within the value stream is shown. There is no standardized flow of communication, as communication can flow in any direction. So there's no saying left to right or right to left. It could be in any direction. Timeline and travel distance. These are timeline appears at the bottom of the value stream map. At the end of the value stream map, below by the end of the symbols and everything, you will see some section where we have the time-related data measurements, such as the cycle time, the waiting time, etc., etc. And the other line placed on the bottom of the flow shows the travel distance of the product or work of the people moving through the process. Okay, let's take a look here. As I said, there are 3 segments in the value stream map: the first, the second, and the third. Okay, so this is The flow of material, this is what we call it the production or process. This is the process. Okay. Now this up here, this is the communication info or communication. On the third, this is what we call it is the timeline. This is the timeline. One more time, in the process, you will see exactly what is happening to create the product. Process A, process B, process C until shipped and send it to the customer. In the information or communication section, you will see how this is get communicated between the company and the customer. It could goes in any direction. In the process should go from the left to the right. The time section here, you will see the time travel for the product. You will see some important feature such as the date and the time to find out what would be the lead time, what would be the processing time. In order to be able to create the value stream map, you should be able to be familiar with the symbols that we use. For example, this first one represent the external company, such as the supplier. Data books, data box here. Level load, MRP, pull, shipment. Now I'm going to focus on just the most important thing. I want you to focus on the external. I want you to focus on the pull. This is a technique whether we pull or push. Push, you push you make and you push it to the market. Pull, you wait for the customer to order from you and then you make it to the customer. And shipment, this is important as well. The flow of material. Inventory, triangle with the eye inside it. Some of the lean concepts you probably want to be familiar with is the production Kanban, withdraw Kanban, first in, first out. A cell, combining more than one operation at once. I did put something here on the right side as well. What I want you to be Kaizen burst. This is important to create the future map. Kaizen burst is later on when we do the improvement. We study the current map and then we start creating the to be or the future map. And that whenever you see a process or a room for improvement, you should create the Kaizen brush saying, okay, here's will change over. We should look into that. So this is just a highlight that will tell you there is a future change going to be happening on this based on what we studied. Again, this is important. The push. Here's an example of the data box. What you should include in the data box: cycle time, uptime, other things as well. Outsource. This is like a shipment, supplier, other things. So I did also listed some link here where you could go to this link and become familiar with more of these symbols. Okay, how we could create a value stream map. What you need to do is, first of all, identify the value stream. Each product line or product family might be considered a value stream. It is difficult to break up products into families sometimes. If it's difficult, set of a part number or product has 70% or more commonality in operation process, it can be considered a value stream. Okay, let me explain this in more details. Now, sometimes it's really hard. We create too many similar products. Now, what if you want to create a value stream map, look into the similarities. If it's 70 or more similarities in the process, then you should create a product map. So in order to create, to identify the value, the streams, what you do, you use something called product matrix, product A, B, C, D, etc. And you see what is the common, how common they're using these steps, the operations. Are they using step number 1, 2, 3, 4, etc.? And then you start xing these and you find out the similarities. This is what we call the product matrix, and this is a very helpful tool to identify the streams. The second thing, the second step for creating the value stream map, you map the current state. You look, observe the process, and you start drawing what you see from the floor. Of course, what you need to do, you begin drawing the external customer and supplier on the top of the page. So on the top of the page, you create the external supplier. Draw the supplier icon, which is, this is the supplier icon. On the upper left, you draw the supplier on the upper left and the customer on the upper right hand corner. Then list down the requirements. What are the requirements? All right, number 3, identify the main process. Create a process box, and it's basically a box like this, a rectangle. This is process A. And then create a box, a process box for each process. A process box in a value stream is an area of material flow in which there are no significant delays or inventory. Wherever there is a delay, there would be a new process box. So whenever you see there's a delay, that means that there's an indication that this is a new a process. You have to have a new box here. Number 4, after we identify the process, we must identify the matrix to be collected. At the minimum, we should include process time, the amount, which is the amount of hands-on operator time, and the amount of machine time spent on one unit this is what we call the processing time. Inventory. And inventory could be identified by this triangle. Inventory includes a count of any inventory waiting between processes. Lead time. Lead time is elapsed time through a process. It includes waiting time up front as well as processing time. Lead time is calculated in one of 2 ways. Here's how we could calculate the lead time. Dividing the inventory between 2 processes by the number of units consumed per day by the customer. Here is an example. If we have 100 units waiting and we sell 25 units per day on average, we have about 4 days of lead time. Again, you have 100 units waiting and we sell 25 per day. That means we have about 4 days of lead time. 4 days of lead time. Measuring the actual lead time for a process, we should measure the elapsed time from when the process received the material from the previous process until the material is completed, processed, and moved to the next stage. Okay, so what you need to do, you have to measure the elapsed time when a process received the material from previous until the material completely processed and moved to the next stage. This is what we call the lead time. So either you divide the number of units, and you have the number of units consumed by the number of units per day by the customer. Divide the inventory between the 2 processes by the number. So again, the example is very clear here. You could use this, or you could measure the elapsed time when how long it will take you to process starting from receiving this material until leaving to the next phase. Also, there are other concepts and measures that you need to be familiar with, such as the yield, percentage of defect per unit, DPU, etc. These are quality metrics for manufacturing processes, typically for administrative processes. Percentage complete and accurate or what we call the percentage CNA, is very useful. Number of operators, this is the number of people working available in the process. Available working time, this would be defined as how much time per day or per shift is available for the process. We would take the entire working day minus breaks. So breaks are not calculated, it's not counted, or any meetings, planned meetings, planned cleanup time, and any other planned activity that takes time away from the process. Change time, change over time. This is a setup time between different product runs on a machine. What is the change over time? How long will it take us to make the machine ready for producing? Machine uptime or reliability. This is the percentage of time that the machine is available and it's not down for maintenance or repair. Uh, Alternatively, overall equipment effectiveness, or what we call the OEE, may also be used as a matrix, which we calculate by the availability times the performance times the quality rate. We'll take an example on this, not here, maybe in a different video, but this is an important concept you should be familiar with, the OEE, or the overall equipment effectiveness. You should multiply the availability for the machine time the performance for this machine times the quality rate, what's the defect rate, and take the quality rate. And we will take an example on how we calculate the OEE, because this is one of the questions in the Lean Six Sigma. Number 5, step number 5 for creating the value stream map, add any other data left to complete the map. Number 6, for you have to plan for the future status map or the to be map. Information gathered become the basis for your future. So now you collected all the data, you completed the map. Now this information will be the base for your improvement, the future for improvement, the future map. Identify the areas of overproduction. What there's an area of overproduction, you have to identify it. If there is any waste in the current production system, you have to identify it and create an action plan to implement the ideal production path. So these are some of the tips that we could use to create the value stream maps. Let's move on 2 more slides here before we end this video. Number 1, I want to talk to you about the buffer inventory is used to reduce incidence or severity of stock out. So some of the question will ask you about the buffer inventory. What's the difference between the buffer inventory and the safety inventory? The buffer inventory is used to reduce the incident of severity of stock out situation. However, the safety inventory is used to protect downstream operations from being starved. So there are 2 different concepts, and you should be aware of these 2 different concepts. One is the buffer inventory and the safety inventory. One, the safety inventory is to protect the downstream operations from being starved to become out of control process, or the buffer inventory is to reduce the severity of stock out situation. The value stream can be used to identify where is the Kaizen builds. We talked about this. The whole idea is to use the current state map to develop a future or to be a value stream map. On-time delivery is another measure that we could use that I want you to be aware of it. On-time delivery can be calculated by dividing the on-time units by the total units. Reliability of the system would be multiply the reliability of the first segment times the reliability for the 6th segment times the reliability for the 3rd segment, all the way until the reliability of n of x. So this is how would you divide or how would you calculate the reliability of the system. Value stream map is a tool for documenting a business process from beginning to the end with a lot of details. As you see, we've went all the way details into seconds, how many seconds we need to or we need to produce a specific item. It is important to quickly identify where you start and where to stop. This is important. And the first step is to identify the stream. And sometimes it's important, it's very difficult to identify that. And this is what we use the process map. If you remember the production matrix, the production matrix is one way to identify the streams. Sometimes it's very easy to drift in and out of other value stream. Because why? Because we're having a multitasking world. We have employees who are working on a different station, different processes. So sometimes things get mixed up, and you have to be able to avoid this and be focusing on one stream. Again, it is important to quickly identify where you start and where to stop with the map, because it is very easy to drift in and out of other value streams due to the intertwined multitasking world of employees who work in and with a transactional process. If there are subtasks or parallel tasks, they should be drawn from left to the right beneath the main flow. So sometimes we have a subtask inside one process. So what you need to do, you have to draw it from left to the right, as we do, because it's a flow, and we put it beneath the main flow, all in separate task boxes. So it's gonna be its own separate task boxes, process boxes. Last thing about the value stream map, I want you to be familiar with something called terminators. Terminators are used in a value stream map, and this is to clarify, rework, move the work back in the value stream without having to draw a line that go against the direction of the main flow, and to connect value streams together. So there are a lot of purposes for using the terminator, and this is the oval, basically an oval shape. And again, we use the terminators to clarify, rework, move the work back in the value stream without needing to draw a line or an arrow against the direction of the main flow. And number three is to connect value streams together. So maybe this sheet would not fit into having different value streams. So you could say, go to page 2, go to page 3, using the terminator. So the terminator will help you. So here we used it in this chart to sales order configuration. So and this would be this basically will go to sales order configuration. So we'll go to sales order configuration. So right here, we'll go back. Basically, we're saying, okay, go back here, but without drawing that line. All right, well, that's it for this video. I think we covered all the measurement tools that we need. Now we're going to look into the next phase. The next phase will be analyzed. Now we have to look into the process. Now we have a well-defined process. We have the baseline process capability. We have some measures on the cost of poor quality. We have a lot of measurements and matrices that we use, such as the cycle time, such as the lead time. We looked into the process, into more details, and now we have a well-defined process. Because of this well-defined process, now we are ready to dig deep into the process in order to analyze it and find some suggestions for these problems, some improvements. We need to analyze these well-defined problems in order to conduct some testing, some hypothesis testing, to create some potential causes, why these causes happen. I'll see you in another video. I'm gonna stop right here. I hope you learned something about the measurement phase in Six Sigma. See you.